Welcome to ECE 2300. In this lab, we will take a brief look at transistors. Two types of transistors will be used: the bipolar junction transistors and MOSFET transistors. Bipolar junction transistors come in two flavors, NPN and PNP. This is a reference to the order of the negative and positive junctions that make up the device. You may think of these transistors as current amplifiers. Each transistor has its own gain factor for current, called beta. Beta is a designed-in characteristic of the semiconductor device. The current flowing in the collector is equal to the current in the base times this beta parameter. A typical value for beta would be 100 to 400. Because both the collector and the base current flow into the emitter current is equal to 1 plus beta times the base current. When designing circuits with bipolar junction transistors, it is important to know the base to emitter voltage, or VBE. A typical VBE value is 0.65 volts. For the NPN transistor to turn on, the base voltage must exceed this value before any current will flow through the collector and the emitter. For the PNP, the base to emitter voltage is the same, but for this transistor, the base must be brought at least 0.65 volts lower than the emitter before the current will flow between the emitter and the collector. We will see this in the current source and current sink applications later in the lab. MOSFET transistors operate on a completely different principle. The gate voltage modulates the channel width between the source and the drain. This changes the resistance and allows current to flow. The relationship between the gate voltage and the source to drain current is called transconductance and is analogous to the beta of a bipolar junction transistor. The difference is that the MOSFET is a voltage-controlled device as opposed to current-controlled. Although MOSFETs can be used in a linear mode, for the most part they are used as switches. A MOSFET is typically fully on when the gate to source voltage exceeds about 2 volts. For an N-channel MOSFET, the transistor is fully on when the gate to source voltage exceeds 2 volts. For a P-channel MOSFET, the gate must be 2 volts less than the source for the transistor to be fully on. In our discussion of MOSFETs, we are referring to enhancement mode MOSFETs. In these devices, increasing the gate voltage increases the source to drain channel width, and thus the current. There is also a depletion mode MOSFET, where the channel width is reduced by increasing the gate voltage, but these devices are beyond the scope of this lab. This week, we will look at bipolar junction transistors as a current source and a current sink. For the third circuit, we will use the MOSFETs to implement a high current power switch. You will need quite a few supplies this week. You need these values of resistors in these quantities. These are the transistors that you will need. You just need one of them. Don't be surprised if these get destroyed in the process. That's why you have 2 of each. Transistors are not the most robust active devices, particularly the MOSFETs, so it's okay if you lose 1 or 2. For your equipment, you will only need the breadboard, the digital multimeter, and the power supply. You will also need quite a few more banana to mini grabbers and banana to banana cables for the power supplies and the digital multimeter. For the first 2 circuits, you will need to use the positive power supply set up for plus 12 volt and the digital multimeter to measure current. Throughout the course, you have been asked to perform circuit analysis that has included constant current sources. In mechanical engineering, many sensors that you will use require a current source to operate. These include temperature sensors as well as most accelerometers. In biomedical engineering, all nerve stimulation is done with constant current. Today, you will see how to design both constant current sources and constant current sinks. Bipolar junction transistors can be configured for a constant current sink and a constant current source independent of the load resistance. Since there is a fixed voltage relationship between the base and the emitter of 0.65 volts, you can set up the base voltage and thus the emitter voltage to a certain value. Then the resistor value in the emitter completely determines the current through the collector. The current that flows through the emitter will be constant and equal to 1 plus beta times the base current, IB. Beta times IB will flow through any output load resistance that is connected to the collector, regardless of the value. The limitation is the overhead voltage on the load. The constant current will saturate once the 12-volt supply limitation is reached. For the current source, calculate the emitter current by taking the base voltage, adding VBE to come up with the emitter voltage, and finally divide 12 volts minus the emitter voltage by the emitter resistor for the calculated value. The difficult part of this calculation will be to find the base voltage. Note that the 20K resistors form a voltage divider. The upper resistor is in parallel with the 499 ohm resistor, but because the transistor's emitter to base junction is also in the loop, the parallel resistance to the 20K ohm resistor will be equal to beta times the 499 ohms. For circuit analysis, assume that beta is equal to 250. Find the parallel resistance of 20K and 250 times 499 ohms. Use this parallel resistor value instead of the upper 20K resistor and calculate the base voltage using the voltage divider equation. Once you build the constant current source, you will use the digital multimeter as an output load in the collector. Be sure to insert the meter in series before powering the circuit to make your current measurement. This measured value should be very close to the current that you calculated. When you connect the PNP transistor, you will need to know which of the 3 pins is the emitter, base, and collector. Looking at the flat surface of the transistor, the pins from left to right are emitter, base, and then collector. Remember that the arrow is always on the emitter in the schematic symbol. Now build the current sink. Be sure to use the NPN transistor. Notice that the emitter resistance is different for this circuit, so you need to recalculate the emitter current and then measure the collector current. When calculating the collector current, remember that the emitter voltage is 0.65 volts lower than the base for the NPN transistor. Just like the previous circuit, this circuit can be used as a constant current sink independent of load resistance. Sink implies that the current is drawn or pulled through the load as opposed to driven into the load. The order of the pins for the NPN transistor is also emitter, base, collector, going from left to right when the flat side is toward you. Record your calculated and measured values in this table. For the final circuit, you will need to use the positive power supply again. You will also need to use the 6-volt supply to control the gate voltage for the N-channel MOSFET. Use the digital multimeter to measure current as well as voltage. Please follow the directions on the slide for this test setup. Be sure to connect the ground from the supplies together. In other words, you're going to use a black banana to banana cable to connect this common on the single supply to this common on the dual supply. And then you can plug the black mini grabber cable into the back of the banana connector or the hole on the side of the banana cable. This way you only need a single mini clip for ground that goes to your circuit. This circuit is often used when you want to use a digital logic level to control a high current signal, such as a power supply, without loading the logic signal. For your 6-volt supply, use the plus 25 dual supply output set up for 6 volts. For the logic signal, you should use the single 6-volt supply set up for 5 volts. To measure the current in series, you can run the 6 volt, that is the plus supply, directly to the digital multimeter using the red banana to banana cable, and then go from the multimeter to the circuit. Here's how this circuit works. With the circuit off, this 100k ohm resistor pulls the gate up to the source potential, keeping the P-channel device off. Once the gate of the N-channel MOSFET is above the turn-on voltage, the gate of the P-channel transistor is pulled down to ground, and the P-channel MOSFET, which is capable of high current, conducts from the 6 volt supply to the load. And oh, by the way, the 7.5 ohm load resistor will get quite warm once you power your circuit, so you do not want to leave this circuit powered for an extended period of time. Please be sure and return the resistor to the lab monitors when you're finished. For the power MOSFET, which is a P-channel device, the pin order is gate, drain, then source, looking at the front of the transistor. Note that in the schematic, the arrow is always on the source of the MOSFET transistor. The arrow points out for a P-channel device and in for an N-channel device. The way that I remember this is that in sounds like N. For the smaller N-channel MOSFET, the order is different. It is source, gate, then drain as you are looking at the flat side of the transistor. For your first measurement, apply 5 volts to the gate of the N-channel MOSFET and measure the current that flows through the P-channel MOSFET to the load. For the second measurement, decrease the N-channel gate voltage and document the minimum fully on voltage for the circuit. We will define fully on such that the source to drain current in the N-channel MOSFET is greater than 90% of the full value that you measured in the first part for this circuit. Record the value for the current you found in the first part in the first row, and for the turn-on voltage in the second row. This concludes the PowerPoint portion of the lab. Be sure that you show all of your tables to the lab monitors to make sure that you got the correct results. I recommend showing each table individually at each step of the lab before you proceed to the next circuit.